Calorimetry is the measure of the heat flow into or out of a system of chemical and physical processes. In a calorimetry experiment, the transfer of heat between the system and surroundings is equal. Oh god, there's more. The insulated device used to measure the absorption or release of heat in chemical or physical processes is called a calorimeter. This is supposed to be a calorimeter, I guess. The one I'm kind of highlighting is when we're working on it in class, I heard. Looks kind of like it's made out of cups. And this one's a bomb calorimeter. Not sure what the difference is. Thermochemistry, or enthalpy. Enthalpy. Enthalpy helps the energy calculations for reactions more convenient and under conditions of constant pressure. Triangle H, small p equals heat. Oh yeah, that's supposed to be the change in enthalpy. Yeah, I'm just not going to do this because I suck at math.
Okay, so I'm going to help out with example 4, enthalpy changes. Okay, so example 4. When 25 milliliters of water containing 0.025 moles of hydrochloric acid at 25 degrees Celsius is added to 25 milliliters of water containing 0.025 moles of sodium hydroxide at 25 degrees Celsius in a foam cup calorimeter, a reaction occurs. Calculate the enthalpy change in kilojoules during this reaction if the highest temperature observed is 32 degrees Celsius. Assume the densities of the solutions are 1.00 grams per liter and that the volume of the final solution is equal to the sum of the volumes of the reacting solutions. This is a crazy big problem, okay? So I'm going to break it down for you in the steps that you need to do. So the first step, we need to figure out the volumes. And remember, we're using our Q equals MCAT equation. So with our MCAT equation, we want to be able to plug all the information in to solve for the enthalpy change. So we want to know the Q, because enthalpy is heat or energy, okay? So we're dealing with liquid water here. So that tells us that our C of liquid water from our table on page 4 of the note packet is going to be 4.184. Yeah, that's terrible. Joules per gram degree Celsius. So that's important for later. We're solving for Q. We can figure out a change in temperature, and we need to know mass. Okay, so we're first going to solve for mass, since mass comes first in the equation. So to solve for the mass, we are going to use the volumes of the solution. Okay, so the first step, solving for M using volume. We know that we have 25 milliliters of one solution added to 25 milliliters of the other solution. So for our volume total, we have 25 milliliters plus 25 milliliters to give us 50 milliliters. Okay. Well, you see where it says, assume the densities of the solutions are 1.00 grams per liter. And that tells us that for every 1 gram, it's equal to 1 milliliter. So what we can do is we can take off the milliliters, and that's going to equal 50 grams. So this is our mass. That's our M for the equation. Okay? So now we can fill in mass to our equation. We know what C is, so we can go ahead and put that in. And then last but need the change in temperature. So, to calculate the change in temperature, we need to know what's the initial, and what is the final. So, if you read through and look, we have 25.0 degrees Celsius, another 25 degrees Celsius, and a 32 degrees Celsius. Well, the 25 and 25 just mean that both solutions start out at the same temperature. So T1 is going to be the 25 degrees Celsius. The T final, or TF, will be the 32 degrees Celsius. So that means to find the change in temperature, we're going to take 32 minus 25, and you get 7 degrees Celsius. So that's our change in temperature. We can plug that into our equation. Alright, so then we can solve for Q. So if you take 50 times 4.184 times 7, you should get very close to 1,463 joules, or somewhere close to that. Alright. But we don't know, we need to know this in kilojoules, not joules. So we have to convert to kilojoules. And there are 1,000 joules in every 1 kilojoule. So just like from milliliters to liters, we're going to move our decimal 3 times to the left. Okay? So we're just going to go 1, 2, 3. So that means that Q equals 1.463 kilojoules. Alright, we're almost there though. Enthalpy can be positive or negative. So in order to know if it's positive or negative, we have to know if it's endothermic or exothermic. So let's figure out if it's endo or exothermic. Well, what's our system? And what's our surroundings? Okay? We are studying what's inside the cup. What is the reaction that's taking place? So the system is going to be the cup, or you could say reactants, or something like that for the system. And the surroundings are going to be everything outside of the cup. Okay. The way that we can tell how the heat is flowing is by the temperature change. Okay, so according to our system and reactants and surroundings, we have an increase in temperature because we start at 25 degrees Celsius and we end up at 32 degrees Celsius. Okay, so we are actually increasing the temperature. If there's a temperature increase, that means that heat is leaving the system. And if heat is leaving the system, so that means that it's flowing from the system to the surroundings, that means that it's leaving, so that means it's exothermic. And if something's exothermic, then we are going to have a negative change in enthalpy. Okay, so with a negative enthalpy, that means that we're going to have the same number that we solved for, but we are going to have a negative number for it. So instead of 1.463, we're going to have negative. And let's run to sig figs, and in this problem, there's 2 sig figs because of our moles, so our answer will be negative 1.4 kilojoules for our final answer. Alright, now we're going to pause and do numbers 8 and 9 in the homework packet, and after we're finished with that, we will keep going in the notes.
Thermochemical equations. In a chemical equation, the enthalpy change for the reaction can be written as either a reactant or a product. For an exothermic equation, the heat will be written as a product. For an endothermic equation, the heat will be written as a reactant. A chemical equation that includes the enthalpy, I said that right?
Enthalpy.
Okay. Change is called a thermochemical equation. For example, calcium oxide is an ingredient in cement. When mixed with water, the reaction to make concrete releases 65.2 kilojoules with the calcium hydroxide. Blah, 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 bunch of letters. You can see them alike. Yeah. Also, fun fact, when making the Hoover Dam, a lot of heat energy was released from the concrete, so they had to actually put in a huge piping system on the inside to cool everything down using water from the lake they were trying to dam up. Awesome, right? Don't think anyone cares. And endothermic. Baking soda, sodium bicarbonate, decompresses when it is heated. The carbon dioxide releases in the reaction, causing muffins, cakes, or breads to rise while baking. I could really go for a muffin right now. Not gonna lie, that would be kind of awesome. And more letters and numbers. The heat of reaction, triangle H, is the enthalpy change for the chemical equation and can be written as follows. CaO, or calcium oxide, that's right, soluble plus water, liquid, would turn into calcium hydroxide, which is aqueous. Triangle H, negative 65.2 kilojoules. Or, that's,
Sodium bicarbonate.
so okay, 2 sodium bicarbonate would turn into sodium carbonate and water plus carbonate, right? That's carbon dioxide. That would be 85 kilojoules. Remember, triangle H will be negative for exothermic, and triangle H will be positive for endothermic. So with exothermic, it'd be like losing energy. With endothermic, it'll be gaining energy. Just keep that in mind, you know? Just saying. Enthalpy changes. The amount of heat released or absorbed during a reaction depends on the number of moles of the reactants involved. This means the coefficients previously used for mole ratios are extremely important. I really hope we don't have to do that math again.
Okay, so our last example for the day. Calculate the amount of heat in kilojoules required to decompose 2.24 moles of sodium bicarbonate. Well, hopefully you wrote this down when Connor was talking about it, but the sodium bicarbonate decomposition reaction is up at the top of page 7. Okay, so I'm just go ahead and copy that down right now. Okay, so now, like Connor mentioned, the coefficients are important, okay? We are starting with 2.24 moles of sodium bicarbonate. So I'm going to go ahead and put that over 1. We have a little bit of dimensional analysis today. And the sodium bicarbonate is the reactant. So, then, we can use the change in enthalpy, the delta H, or triangle H, and this will help us to figure out the amount of heat. Okay? That's going to go on top of the next step. But we need to know moles on the bottom so that we can cancel out the moles of our sodium bicarbonate. Well, where does that number come from? It comes from the coefficient in front of the reaction. So we have a 2. So that 2 is going to be 2 moles in the bottom. So now the moles of sodium bicarbonate cancel out. We're left with kilojoules, which is what the problem is asking for. So now we can go ahead and solve. So if you take 2.24 times 85 divided by 2, you should get 95.2 kilojoules, but that's not in sig figs. So we had 2 sig figs in our 85 kilojoules to start in our change in enthalpy. So that means that we're going to round to 95 kilojoules. And that is the amount of heat required to decompose 2.24 moles of sodium bicarbonate. Okay, so now we can do numbers 10 and 11 on the homework.
Yeah, shout out to Mary Beth, who keeps begging me for a shout out. And also shout out to Allie Lawler, who Mary Beth is also begging for me to shout out. Yeah, bye, this is Connor Trito, and this was not fun at all. Not as fun as I thought it would be. So, yeah.